All right, hi everyone. So, welcome back to video formats. Again, this is going to be a replacement video for discussion next Friday, the 14th, as again, I will be out of town for a personal matter. I'm going to a wedding, a friend's wedding in Austin, Texas, and that's where I'll be. So here I am recording a video and hopefully uploading it well in advance so you guys have time to look over it and practice through the material of it, because in this setting I can do more practice problems and you guys can pause before I go over the answers, and it'll be hopefully more practice as I walk you through the examples. And you can also play and pause and replay stuff back. And yeah, so let's go ahead and start with the logistics for this week. So today I'll be covering the stuff that I didn't get to cover as much as I wanted to from the previous lecture. So, in terms of logistics for 11:14, or whenever you see it, hopefully it's before 11:14, we're going to work on stuff from 3.5 and 3.6, and some practice problems that we didn't get to in discussion. And then the actual thing that's on schedule will be the last sections that are going to be covered on the exam, so 4.2 and 4.3. And the corresponding ALEX will be due on the 16th, so the corresponding Sunday of this week. And again, no discussion on Friday, so if you guys come, I mean, you guys can use the room if you want to study in there. It's the book time, but you guys can also just stay home. The last thing is that your upcoming midterm 3 is coming up on the 18th on 3.1, 3.2, 3.5, 3.6, 4.2 and 4.3. Okay, so 3.1 is week 1, 3.2 to 3.6 is week 2, and then this is week 3. Okay, so this we'll be talking about exponential and logarithm functions. But first, let's go back and do a recap on 3.5 and 3.6. All right, so if you want to skip it past, I'll put a marker in the video to skip past if you're already familiar with this, but let's go over it again for good measure. So we'll start with the definition. This is going to be 3.5, a rational function. So recall that a polynomial uh, f is of this form. Let's call it a polynomial h, for example. H is a polynomial if it has this form. an xn plus an minus 1 xn minus 1 plus dot 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 until a1 x1 plus a0. So in this case, we call h as a polynomial of degree n. Okay, n in this case is a positive whole number, a positive integer, and your an's are going to be just any real number, positive or negative, but non-zero, hopefully. You just need an to be non-zero. Okay, so that's a form of a polynomial. We need this because to define a rational function, take any p of x and q of x to be polynomials such that f is rational if I could express f as the ratio of these two polynomials. There's division, as so. And so we have division. We also need the restriction that q cannot be 0, as so. Okay? But since q is a polynomial, as we said before, q most definitely can have zeros, right? There's places where q can be 0, and that would be division by 0. And so in terms of rational functions, this is where we would like to introduce the notion of a vertical asymptote. Okay? So a vertical asymptote, I'll define a vertical asymptote. A vertical asymptote, or let's say a vertical line, x is equal to c, is a VA of f if if x approaches c from the left or the right, your function diverges to either plus infinity or minus infinity. So graphically, if I draw a coordinate plane as so, and I say that this is c, and asymptotes are denoted by dashed lines, as my function approaches c, it either diverges up to infinity or down to negative infinity. And any combinations of this will be the case. Okay. So in terms of the graph, and what I want you guys to be vigilant on is to never have your graph intersect the vertical asymptote. Why? Because if your solid line, if your solid graphs, if these functions that you draw intersect the dashed line in some way like that, what you're asserting is that you can divide by zero, which is not possible. So put a star here and say that graphs cannot cross VAs. Okay? If you cross VAs, you'll get automatically penalized and your graph is basically voided in that case. All right? And since this is division by zero, if F is P over Q, you can find VAs by solving Q of X is equal to zero. As in, set the denominator equal to zero, solve for the X values, and those X values will be where your vertical asymptotes are. Okay? So for example, if I have the function, let's say g of x is equal to 1 over x plus 1, x plus 2, x plus 3, like so, you can immediately assert that there's going to be VAs of g at precisely x equals minus 1, x equals minus 2, and x equals minus 3. Okay? VAs are vertical lines, so the equations of the VAs will be always x equals. Okay? Good. And then the way you graph is, of course, with dashed lines. So if I draw a coordinate plane, without actually drawing the graph, I can draw the vertical asymptotes. So this is minus 1, minus 2, and minus 3. You're going to have dashed lines at minus 3, minus 2, and then minus 1, as so. So x equals minus 3, x equals minus 2, x equals minus 1. Okay? All right. Now, since we have the notion of a vertical asymptote, it makes sense that there must be some notion of a horizontal asymptote too. So that's what we're going to talk about next, or talk about again, because we've already done this formally. So 3.5, a horizontal asymptote. So the definition is such, right? The vertical line y equals d is an HA of f if, as you approach as you approach the extreme ends of your graph, so plus or minus infinity, extreme left or the extreme right, your function f of x is going to limit to this d value, right? So graphically, what does this look like? I'll draw my coordinate plane and draw a dashed horizontal line and call it y equals d. What I'm saying is you have your function, let's say in red, and it approaches it some way, and I can also cross, it's going to limit to your asymptote like a magnet, right? So as you can see, like in terms of how these graphs function, your functions will be pulled towards these asymptotes like magnets, but usually they're never going to cross it. So if you for in terms of VAs, you can't cross it. You'll get infinitely close. But for HAs, you can cross, right? HAs, you can have an intersection at a finite amount of points. And that's non-trivial. You can actually use that to self-solve, as we'll see in a couple examples as we get to moving after talking about the HA a little bit more. But yeah, the HA, basically the same idea. As you take to the extreme ends, you're either approaching from the bottom or the top towards this y equals d value. Let's show. And in terms of finding the HA, we need to define a little bit more, right? We said that f, rational f, is just a ratio of p and q, but let's be a little bit more specific and say that f is a ratio of an nth degree polynomial and an mth degree polynomial. So bm xm plus b0, okay? And so we consider the three cases. So case one, if n is larger than m, as in the degree of the top is larger than the degree of the bottom, the top degree dominates and there will be no HA. Okay? Right. So let's say if I have x cubed over x squared, well, by the first week of the semester, we know that this simplifies to just x. And clearly, this x just goes to infinity as you take x to be larger and larger. Right. So there's not really a limiting value because you're diverging off to positive infinity. Same thing, if I put a negative in front, it goes to negative infinity. So if n is larger than m, you have no HA. Okay? From high school, probably, if you guys touch on it, you might have no recall that this is the case of maybe a presence of a slant asymptote, where you need some polynomial division, so long division or synthetic division. We won't get that. We won't go into that in too much detail because we haven't formally taught polynomial division or gone over it, so you don't have to worry about it. But in terms of classifying if there's an HA, we can do so. In this case, if the degree of the numerator is larger than the degree of the denominator, you're going to say there's no HA. Okay. For case two, we have if n is equal to m, then there's going to be an HA at y is equal to the ratio of the leading terms, an over bn. So in our case, let's say that if I have a rational function that looks like this, let's say I have 4x to the 6 over 7x to the 6 plus 1. We know that n behavior deals with only the leading terms. So really, this is basically equal to 4x to the 6 over 7x to the 6 if you take x to be really large. That addition of 1 isn't going to matter too much if you take x to be really large. And then by week 1 standards, again, the x to the 6 cancel, and you're left with 4 over 7, which is simply just the ratio of the leading coefficients. The leading coefficient of the top is 4x to the 6. The leading coefficient of the bottom is 7x to the 6. So yeah, so the HA will be at y is equal to 4 over 7 for this particular example. All right. And then for case 3, I have if n is less than m, then my HA will be at y is equal to 0, as in the denominator degree is larger. So to go back, let's say I have 4x to the 6 over 7x to the 7. Well, this simplifies to just 4 over 7x, and then it should be relatively clear to see if you take x to be really large, you're going to see that the bottom blows up and you're going to have a fixed number over a really large number. It's going to be a really small fraction that gets closer and closer to 0. So this limits to 0 as you take x to go to infinity. And that's why there's an HA at y is equal to 0. Okay. So in terms of examples, we would also like to think about graphing these rational functions, and we have some steps that we would like to do. Okay. So, but to keep in mind, again, we can't pass through VAs, but we can pass through HAs. Okay? It's not so we cannot pass through any vertical asymptotes at all in any case. That would be division by zero. But there are certain cases where we can pass through HAs. It's not going to happen all the time, but there are certain cases where we can. All right? So, yeah. And so I think that's it. So we can talk about graphing now. So since we were graphing, we have some general steps that we would like to do. So first, every single graphing problem, it's always going to be some form of finding the x and y intercepts. Intercepts. Okay, so that's what you do. We know how to do that, finding x and y intercepts. Two, you find the the vertical asymptote. It's very easy to find the vertical asymptote. You just set the bottom equal to zero. Just there it is, and then graph. And then graph these. Graph VAs. Three, we're going to consider finding the HA now. Finding any HAs. And we graph it as a dashed line as well. So graph HA. And then four, since we said that the function can pass through the HA possibly, we're going to check if it does. So you're going to determine if function passes through HA. Okay? And then finally, we're going to use symmetry as in we're going to use the shapes of the parent functions 1 over x or 1 over x squared and then plot points to graph the function. Okay? So what are the parent functions look like? I think I've drawn it a couple of times before, but this is what it looks like. So 1 over x looks like this. It has this shape. Sorry, so 1 over x. And you can't see it, but if you look carefully and maybe also try to see it explicitly, you can see that, well, one, if I set the bottom equal to zero, I have a vertical asymptote at zero. That's why these two, as I approach from the left and from the right towards zero, I'm going towards infinity. So that shows you the definition of the vertical asymptote. Also, since the degree of the top is zero and the degree of the bottom is one, or is two, actually no, just one, my bad. This is supposed to be just x squared, or no, just x. Since the degree of the bottom is larger than the degree of the top, there's going to be an HA at y is equal to zero. So you can see that as you go to the extreme ends of the left and the right, your function is going closer and closer to zero from the top and the bottom. Okay, so we're going to use this image. You could also use this image too if your graph is even. Right. So this is 1 over x squared. Okay. So by, I think, the last sections for the midterm, transformations and symmetry, you can see that the square term is, of course, symmetric about the y-axis, and this 1 over x term is clearly symmetric about the origin. All right, so the first one is odd, and then the second one, 1 over x squared, is even. Okay. So let's try to go through some examples as show. So the first example for 3.1 or 3.5, 3.5, 3.6 is the following. We're going to graph f of x is equal to 2x squared over x squared minus 4. Okay. So what does this look like? Well, What we said first is what we want to do is to solve for x-intercepts. So let's do so. We want to solve for the intercepts. So you set the function equal to 0. This implies that if I multiply both sides with the denominator, I get 2x squared is equal to 0, which implies x is equal to 0. Okay? So if x is equal to 0 when y is equal to 0, I have an origin point as an x-intercept. So this also implies that 0, 0 is also a y-intercept. And you're done for intercepts. Okay. Next, we find the asymptotes. So to find the vertical asymptotes, you set the denominator equal to 0. In this case, x squared minus 4 is equal to 0. You can factor this as x plus 2, x minus 2 is equal to 0, which implies that I have VAs at 2 and minus 2. As so. Next, if I find my HA, okay. For my HA, I look at the degree of the leading terms. The leading term is 2x squared. The leading term for the denominator is x squared. So 2 and 2, the degrees of the top and the bottom match. So by our rule, makes us say that there should be an HA at y is equal to 2 over 1, which is just y is equal to 2. Okay? Now, the last step is to graph this function, see how it works, right? So if I draw my coordinate plane, like so, I graph my point at the origin and label it. Don't forget to label your axes too. So this is x, this is y. I label my axes and I plot my vertical and horizontal asymptotes. So if I have a horizontal asymptote at y is equal to 2, I have a vertical asymptote at x equals minus 2, x equals minus 2. And I also have a vertical asymptote at x equals 2. All that's left to do now is to plot what happens in the middle, right? Oh, we forgot to do one thing. We forgot to check if the function intersects the HA. We can easily do so. All you have to do is set your function equal to the HA itself. So if my function is 2x squared, 2x squared over x squared minus 4, I'm going to set it equal to this 2. So 2x squared over x squared minus 4 is equal to 2. This is nothing but 2x squared. If I multiply the denominator on both sides, I get 2x squared minus 8. And we can subtract 2x squared on both sides and get 0 is equal to minus 8. But look here, it's saying that 0 is equal to minus 8. That's clearly a contradiction. So we must not have a place of intersection with the HA. And that's going to be the case, right? So if you try to solve the equation, if you set your function equal to the HA and you get a contradiction, you conclude by saying that there is no point where your function intersects the HA at all. Okay? All right. So we verified, we determined that it doesn't intersect the HA, and now the last thing is to use symmetry to check, to graph the function. So in this case, we want to check by symmetry, as in if it's even or odd. So I'm going to sub in f of minus x into the function. So f of minus x is 2 times minus x squared over minus x squared minus 4. We know that this is just 2x squared is equal to over x squared minus 4, but this is just f. So our function is even. That means we can superimpose the left half and the right half of the parent function 1 over x squared to the leftmost half and the rightmost half of my current graph. Okay? Since it has this shape on the left, I can put this shape right here on the left, the leftmost half. Similarly, if I have this shape on the rightmost half of this parent function 1 over x squared, I can superimpose that image in the rightmost half. Okay? I'm going to be consistent here, right? You can see that this half is being sandwiched by this vertical asymptote and this horizontal asymptote. You want to have the shape in that same corresponding spot between the vertical asymptote and the horizontal asymptote. So, okay. So all that's left to do is to figure out what happens in the middle. And how do we do so? Well, you do it by using test points. So I have a point at 0, 0, and I want to see what happens on the left and then the right of my function. So let's test out a point. Let's test out some points. So to the left of 0, I'm going to choose an easy point like f of minus 1. So when x is minus 1, what happens? I have 2 times minus 1 squared over minus 1 squared minus 4. That is simply just 2 over 1 minus 4. And that is 2 over 3. Negative 2 over 3. So that means I have a point at minus 1 minus 2 over 3. Okay. So that's what happened, and where can I plot that? So negative 1 is right here, and 2 over 3, if this is 1, it's a little bit less than 1. So this is my point at minus 1 minus 2 over 3. And by symmetry, you can assert that there's also going to be a point at 1, 2 over, or minus, or 1 minus 2 over 3, 2. So I also have a point here. That's because of the even symmetry, okay? Well, this should already give you a nice shape, right? Because any point that you graph must be intersected. So you can connect these dots right here and see that you have sort of like a pseudo-parabola shape. And by the behaviors of these asymptotes, your function must get pulled to them like magnets, but never crossing because it's a vertical asymptote that they're going towards. So this is the general shape of the graph. Okay. Now, if you don't believe me, I'm going to share my screen uh, over here. Like so, you can see here the graph that I graphed to the same function on Desmos. Okay. So again, you find this half, this leftmost half and this rightmost half by verifying the symmetry. You check if the function's even or odd. If it's even, you superimpose the image of 1 over x squared. If it's odd, you're going to superimpose the image of 1 over x. So since it was even, you superimpose the rightmost half and then the leftmost half onto your corresponding graph. And then for anything in the middle, you're going to just simply use by first principles. You're going to just put in test points and calculate the points by putting your test x values into the function and getting out a y value. And those will be your 2 points. Okay? All right. So let me go back and share my screens as so. So that wraps up uh, rational function graphing. Now what we're going to get into is talking about exponential stuff. Okay, so let's talk about some exponentials, exponential and logarithms. So this is coming from 4.2. So 4.2 is talking about exponential functions. Okay. So we've worked with some special types of functions, but they all similarly look like raising some x term or some special x term to a power of some sort. So you have x cubed, square root of x, x squared, absolute value of x, etc. in these sort of sites. So that's really where x is the base and the exponent is just some number. Okay, whether it be a whole number, a negative number, or even a fraction. Okay, exponential functions looks at what happens if we flip the positions of the two objects. If I made my base a number and my exponent the variable. So that's what an exponential function is. So to formally define it, right, let b be a real number such that b is a positive number and it's also not equal to 1. Then for any x that is real, the form f of x is equal to b to the x is called an exponential function of base b. Okay? So as you can see, the big number being raised to an exponent x, that's called the base. And then of course the exponent is just called the exponent, right? Okay. So we have these functions now, and we can also deal with some properties, right? So one, talk about properties. So the function b to the x will always be positive, okay? It'll always be positive. Why? Well, let's do some cases. Well, it should be obvious if you take b to be, let's say, to any positive number x, let's say 1 or 2 or 71, dot, dot, dot. You're just going to get a bigger and bigger positive number. You're just multiplying numbers together. If, in this case, if b is a positive number, you're multiplying positive numbers with each other, they're going to be positive, right? Um, but if b is negative, let's say -1, notice by your exponentiation rules, your exponent rules, b to the -1 is simply just 1 over b to the 1, which is just 1 over b, right? So if b is a positive number, 1 over b is still going to be a positive number as well, right? Same deal with b to the -2. That's just 1 over b squared. It's going to be a small number, but it's still going to be positive. It's going to be larger than 0. And the same thing, b to the -71 is equal to 1 over b to the 71. So you can see that it doesn't really matter what x values you have, the quantity b to the x will always be positive, okay? And graphically, this gives you the notion of a horizontal asymptote, okay? So in this case, since I can vary uh, x to be the entire real line, we took x to be a whole line, the domain of any exponential function is the real line r minus infinity to infinity. But the range is going to be dependent on your vertical displacement if you have a vertical transformation, a vertical shift. So the range, in this case for b to the x, is 0, infinity, right? So since b to the x is strictly larger than 0, strictly larger, 0 is non-inclusive. That's why there's parentheses here. And you can grow off to infinity, and that's also non-inclusive. And in terms of the graph, your function is going to look like this. Yes, so we know that anything to the 0 power is just 1. So I have a point at 0, 1. And so the general exponential function shape is going to look something like this. Okay? In this case, my HA is, of course, this dashed red line at y is equal to 0. And that's going to be very important, right? Exponential functions can never be, or can never return a negative value, the exponential terms. Yes, if you shift the function down below the x-axis, there's going to be cases where the function is negative, but the exponential term in the function will never be negative. Okay? Because yes, this is a function, you can apply graph transformations to it. So the general idea is going to be the same thing. I have a function f of x, I can write it in the general form of a transformation as a times b to the x minus h plus k. Now let's not use h and k today, computer says. Let's use c plus d. Okay? And it's exactly what you expect, right? A is a vertical scaling. Acts the same way as you worked with 2 weeks ago. X minus c, that's your horizontal shift, which is exactly what you expect. Minus c, that means you're going c to the left, or no, c to the right, c units. If it's plus c, you're moving c to the left. All right, did I get it mixed up? So x minus c corresponds to a horizontal shift right c units. If it's x plus c, it's left c units. So horizontal shifts. And then d is your vertical shift. And it also doubles down as your, this also doubles down as the HA. So the HA is at y is equal to d in this case. And so let's check it out. Let's see what happens by going on Desmos, for example. So if I go on Desmos, and I type in, let's say, 2 to the x, there's clearly a vertical asymptote here at y is equal to 1, or no, y is equal to 0. If I add 1, as I shift the graph up 1, the horizontal asymptote also goes up 1. Similarly, if I shift the graph down 1, my graph HA will go down 1 as well. So your vertical displacement, your vertical shift down or up for your exponential will dictate the location of your HA. Okay, so yeah, you can play around with this in Desmos, and I encourage you to do so. If I do 2x minus 2, my HA is at minus 2. You add, let's say, 21. My HA is, of course, going to be at 21, like so. Okay, good. All right, so that's the HA. Let's go back and now talk about the inverses as so. So let me share my screens. Hold on. Share screen. So let's see what I want to cover. So how do I graph this? For example, let's graph f of x is equal to 3 to the x, for example. Well, you can go about it like this, but we can immediately assert that since 3 to the x does not have a vertical displacement, it's going to simply, what do you call it? Have an HA at y is equal to 0. Equal to 0, like so. So HA is y equals 0. And then you basically graph by first principles, right? So you use test points. So let's go ahead and do so. If I draw my x and y table, and have a couple of spots. So when x is 0, I have 3 to the 0, and that's just 1. So 0, 1 is a point. Let's do 1. 3 to the 1 is 3. So I have a point at 1, 3. 2. If x is 2, I have 3 squared, and that's just 9. So I have 2, 9. So I have those 3 points. I could also graph a third point. X to the 3. 3 squared is 27. You can see this gets really big really quickly because it's exponential. Exponential growth is really fast. It's much faster than linear functions. Yeah. But we could also plot negative numbers too, right? That's what we said before. So in terms of like, say -1, well, 3 to the minus 1 is just 1/3. If x is -2, 3 to the minus 2 is just 1/9. And then -3, 3 to the minus 3 is just 1/27. So the numbers get smaller and smaller as your negative numbers become smaller and smaller, but always terminating to 0, okay? So you can plot these points as so. If you go over to the document on this side, right here, you see that the function f of x is equal to 3x, I make the same table here, and then you simply plot the points, and you get the shape that you see here. And we said before, without even doing anything, we have an HA at y is equal to 0. You can see that it terminates to 0, it never touches 0. And of course, you could graph the same thing on Desmos. So 3x was my graph. What I said before was what 1, 1, 3 was a point on the graph. 2, 9 is a point on the graph. 3, 27 is a point on the graph. It's right up there. So all the points we found are legit. 0, 1 is always going to be a point. That's going to be a fixed point. And of course, the smaller points, right? -1, 1/3. That's on your graph too. -2, 1/9. That's also going to be your graph. You can see that it gets smaller and smaller, but it never actually crosses 0, right? You're always going to be positive. There's no negative numbers down here. And if I wanted to plot the HA, yeah, the black line, let's change it to a dashed line, orange dashed line. You can see that, yeah, the function, you keep zooming in, you don't actually ever cross the x-axis at all. You just get smaller and smaller towards 0 infinitely. Okay, good, 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 good. So, yes. With that in mind, let's now talk about logarithms, right? Logarithms. So we have an exponential function. We gave some definitions on how to graph stuff now. But we also have the notion of a logarithm function, as so. And this concept is usually one of the trickier ones for college algebra students, right? Because it's the main function. The main use of this function is simply to act as the inverse function of an exponential. Okay? So remember what an inverse is. So two functions f and g are inverses of each other if a condition is satisfied. If the forward composition is equal to identity and the backwards composition is also equal to identity. Okay. In this case, that's what a logarithm, the main function of a logarithm is to be this role for an exponential. Okay. So this is now 4.3 logarithmic functions. So if x and b are real numbers such that b is not equal to 1, then y is equal to logarithm x is called, of base b, is called the logarithmic function with base b. Okay. And the following property holds, where y is equal to log b of x. This is the same thing as b to the y is equal to x. Okay. So what am I really saying? I'm saying is that if I want to evaluate a logarithm of some number, this is simply me asking myself, what is the appropriate number to raise the log base to that gives me x? Okay, that's essentially what it is. What number do I raise to? What number y do I raise my base to b to give me the inside of the logarithm? It's called the That's going to be the way you want to think about these intuitively. So some terminology. This b is called the log base. What's ever on the inside, so the parentheses here, we call this the arguments. Okay, so that's some terminology. I'm going to use that a lot. So yes. So let's do some practice. Okay. So for example, log 4 of 16, I want to evaluate this. Okay. So how do I do so? Well, I want to ask myself, what number do I raise 4 to give me 16? It's going to be 2, right? So 4 squared is 16. So logarithm base 4 of 16 is going to be 2. And what I'm saying is this is equivalent to, if I match this equivalence to this, let's see, my base is 4. I'm saying my y is 2, and my x is whatever on the inside, the argument 16. And that's, of course, going to be true. So this is a true statement. You can check. Another example, two examples. Logarithm base 5 of 0.2 is equal to -1. Okay. Recall that 0.2 is the same thing as 1 over 5. So what am I asking myself? What power do I raise the log base to, 5 in this case, to give me 1/5? That's going to be -1. So if I do the equivalence relation, this is simply 5 to the -1 is equal to 1/5, which is a true statement. That's how you know you did this right. All right. Another thing, we can evaluate logs given anything. Let's say that we weren't given an equality sign. If I have log 12 of 144, how would I go about solving this or evaluating this expression? Well, you can think of this like this, right? If you don't know what the log value is, simply set the equation equal to some dummy variable x. Okay? Then you can switch this to exponential form. So you can also say that 144 is really equal to 12 to the x. And what is 12 to the x? Well, in this case, 144 is 12 squared, which is equal to 12x. Since the bases are equal, I can simply just set x to be equal to 2, like so. So in first principles terms, computing a logarithm is simply just an exponent finder. Okay, that's what it really is. So I can also say that log base 8 of 64, that's simply going to be 2, right? What number do I raise 8 to give me 64? That's just 8 squared. And also log 64 of 8, as in what power do I raise 64 to give me 8? Well, we know that the square root of 64 is 8, but the square root is really just 1/2, so this is 1/2. Yes, so it's like you want to switch your thinking in reverse. The main principle is of course this. Let me say it. Let me write it out. What to evaluate logs, think what number do I raise my log base to obtain the argument. Okay? Remember that the argument is what is ever on the inside. So log base b of x. This is the argument again. Okay. And yes. So since we talked about logarithms, we can now talk about some properties, right? So there are some nice nifty properties. The first property that I would like to get into is some formalisms. So there are going to be cases where I give you a log and there's not going to be a base that is explicitly listed. This, of course, is going to be the standard way. Other classes will have different standardizations, but for this class, if there is no log base that is present, you are going to take the log base to be 10. Okay? 2. Now, if I have log base e of x, this is going to be denoted as the natural log of x. Okay, so we haven't talked about e that much, but e is like a number like pi, right? It's an infinite decimal series that's irrational, and it goes on forever. And if you want a particular value, e is approximately equal to 2.7181. Okay, so if I have y is equal to log x, I really mean y log is equal to log base 10 of x. And if I have log base e of x, this is simply just y is equal to ln x, so the natural log of x. 3. Log base b of 1 is 0 because if I switch this to exponential form, b to the 0 is 1. Okay, what number do I raise b to give me 1? Well, raising any number to 0 gives me 1. So that's why log base b to 1 is equal to 0. So yes. Okay. 4. Log base b of b to the x is equal to x. Okay. This goes back to the notion that the logarithm and the exponential are inverses of each other. In by first principles, the logarithm is the inverse of an exponential. It's its main function. So if you want to think about it, log base b and b cancel, just leaving you the x. Okay? Similarly, if I have b to the log base b of x, the log bases and the log base b and the b cancel, just leaving you x. Okay. So what is this really saying? Take f of x to be log of x, log base b of x, and g of x to be b to the x. So f of g is log base b, b to the x, that's x. And g of f of x is b to the log base b of x, which gives you x. And this is how you actually define a logarithm, for real. This is where it comes from. You define the logarithm function in terms of this inverse property because its main purpose is going to be the inverse of the exponential. Okay? So since it's the inverse of the exponential, all of the properties in terms of the graph will be reversed. All the x values would be now y values, and all the y values would now be x values. So remember, for exponential functions, b to the x had domain uh, of all reals, but now the domain of any log is dictated by, instead of a horizontal asymptote, we now have a vertical asymptote, is going to be 0 infinity, non-inclusive. Okay? And then the range is going to be all reals. Okay? So why is this? What is this? Why is this the case? Well, inverses, you're swapping the x and y, right? Remember the algorithm to find an inverse. You're swapping x and y. So now x is playing the role of y and vice versa. So if you compare up here, the domain of any exponential function is the real line. The range is 0 to infinity. And down here, it's the reverse. The domain is 0 infinity, and the range is the real line for logarithms. Okay. So since the domain is restricted, this gives you a sense of a VA. Um, and since it's also another function, logarithms will be uh, sensitive to graph transformations as well. So the general form of any logarithm function is given like this. A times logarithm base b of x minus c plus d. Okay. Where again, a is your vertical scaling, still the same thing. X minus c is your horizontal shifts. So like left and right. This doubles down now as the location of your VA. So your VA will be at x is equal to c. And then d is, of course, your vertical displacement. So vertical shift. So essentially, well, they're all the same graph transformations that you expect. But now with these new functions, we have to deal with these asymptotes as well. So let's see it in action. So I'm going to share my screen for Desmos. As so. So in this case, watch. If I have logarithm, let's say log base 10 of x, you can see that compared to 10 to the x, it's of course going to be symmetric about, or it'll be a reflection about the line y equals x. This is what we expect from the inverse. You can see the reflection here. But in terms of graph transformations and the properties, you can see that at x is equal to 0, there's a vertical asymptote given by this black bolded line. Now, if I, let's say, subtracted 3, I move the graph over 3 units to the right. you can see that the vertical asymptote also moves 3 units to the right. All right, to the left. You can go to the left as well. Let's say we go left 2 units. My vertical asymptote then also moves 2 units to the left. Okay. You can also move this down, up, and down, and vertically scale it as much as you want. But the overall dynamics that's important, or that most significant in our case, is going to be where this vertical asymptote lies, right? You cannot put 0 or any negative number into the log because there's nothing defined over here. It's undefined on the left side of the vertical asymptote. All right. Okay. So in terms of graphing, what you want to do, and this is also on Canvas, is you want to think about changing your exponential form to logarithm forms, right? In this case, my x is going to be given in a form of an equation, 3 to the 0 is equal to 1. So your y's are going to be the exponents, right? Remember, the logarithms is an exponent finder. So whatever you see here in the exponent is going to be the value of the function itself. And it has this picture right here. Yes, so. Okay. But again, to plot these, you simply just put points in. You can see that it reflects about the origin line, and that gives you essentially what you need for logarithms. Like show. Okay. Okay. And I think that is going to be it. Aside from, but let's go ahead and compute this then. That's it. Let's go through it as well. So let's have f of x is equal to what do you call it? Let's do y is equal to log base 3 of x. All right. Or let's graph. Y is equal to log base 3 of x. This is equivalent to saying 3 to the y is equal to x. Okay. So I have two forms now. I have a representation of y and a representation of x. So that's all you have to think about. Okay. So let's say when x is 1. 3 to the y, what gives me 3 to the y is equal to 1, y has to be 0. So x is 1, y is 0. And keep going a line. Let's say I want 3 squared to be 9. Well, then y is 2, right? Exponent finder. So you can write these trivial statements right here, the powers of 3, for example, and the logarithmic value will be precisely the exponent you raise 3 to. 3 squared, so 3 cubed is 27. So x is 37. You go in reverse, right? 3 to the minus 1 is 1/3. So 1/3 to the minus 1. 3 to the minus 2 is 1/9. So minus 2. 3 to the minus 3 is equal to 1/27. So my exponent is -3, so that's going to be my y value. So you can plot these points. Okay. We assert that log base 3 of x has a vertical asymptote at x equals 0. I'm not moving my graph anywhere. There's no vertical or horizontal displacement. So I'm fixing my VA. Then I simply just plot points like I regularly do. So at 1, I'm 0. At 9, I'm 2. So a whole bunch of lines have 2. And you can see that it grows really slowly, okay? And you can keep plotting points, and you have this general shape right here. And your vertical asymptote is given by this line right here, like so. Okay. But to conclude this, let's do an exploration on Desmos and see this happen really quickly. Okay. So let's have log base 3 of x. You can see that it doesn't look like it's growing. It looks like there's some HA, but no, it actually grows really slowly, right? My graph will go really slowly because it's an exponent finder, right? Being the inverse of 3 to the x, the exponential, you can see how slowly it grows. The exponential grows really fast, and this grows really slow. For example, at 2, my logarithm is at 0.62 or 63. But at 2 on the exponential, I'm at 10. So it grows really fast. So you can make an observation that exponential grows fast, they're the fastest, then linear functions grow uh, sufficiently fast, and then logarithms are the least fast, it's the slowest. That's so. That's yes. I think in terms of that, I think this is all you need to know from 4.3. Um, so keep that in mind. Also, keep your eyes peeled for any practice exams that will come out. I'm trying to get that to you hopefully within a week's time, as in a week before the exam. Uh, so yeah, but I think I'll end it here and hopefully see you guys when you take your exam. Right. Okay. Hi again. So in this section, we'll go into more depth into talking about logarithm algebra rules. Okay. So in the previous part of the video, we talked about graphing exponential logarithms and the basic properties um, to these this new logarithm object. But now we're going to talk about the arithmetic that we can do with these logarithmic functions, right? We said that logarithms were indeed the inverse of exponential functions. That's their main function. And two, intuitively, you can think of it as an exponent finder, right? So when I mean log base b of x is equal to y, I'm really asking myself, what exponent do I need to raise this log base b to give me back the argument x? Okay, so recall b is the log base and x is the argument. That's the terminology. And this statement is equivalent to saying b to the y is equal to x, right? It's an exponent finder. And from now on, I will refer to this as the premier example. So this is the most important thing I would say, this most important rule to remember out of like the 4 or 5 rules that you have to be familiar with. So I'll continue citing this a lot. So I'll give this a name called the premier example. So here we go. So there's that's the premier example. The first rule that I like to talk about is going to be the inverse rule. So the inverse rule, we actually already seen this before. I said it before in the previous video, or in the previous part of the video, which basically states that logarithms are indeed the inverse of exponential functions. So if I take the forward and backward composition, I should get back identity. So that's what the inverse rule says, is if I have a log base b, and I'm taking the log base b of b to the x, this should return back just x. And also, if I have b to the x, but instead of x, I put log base b, I raise b to log base b of x, I should also get back identity. So As we continue working on this and solving exponential and logarithm functions, you're going to be composing both sides of an equation at some point in your line of work with either an exponential function or a logarithm function to undo the exponential or logarithm and get back the x that we see. It's a special technique that we use to invert and recover back our independent variable x. So that's the inverse rule. The next rule that I would like to talk about is, of course, going to be the product rule. So that says if I have the log base b of a product xy, where x and y can be any two numbers or two mathematical objects like functions, this is simply the equivalent to saying take the log base of each multiplicand and add them together. So the log of the product is essentially the sum of the log of the multiplicands. So log base b of xy is equal to log base b of x plus log base b of y. Okay, so like an easy example to think about is if I have log base 2 of 32. If I didn't know that it was 5, this does equal 5, but let's say I didn't know it was 5. Well, I can break this up as log base 2 of 8 times 4. All right, so I do know that power. And using the log base rule, I can say that this is equal to log base 2 of 8 plus log base 2 of 4. Where the first one, I'm really asking myself, what power do I raise 2 to get 8? The answer is 3. And the second one, log base 2 of 4, what exponent do I raise 2 to get me 4? That's going to be 2, which is 5. Okay? Yes, that is the product rule in its simplest form. Along with the product rule, we also have the quotient rule. So if I label this the product rule, I also have the quotient rule, which basically states if I have a division instead of multiplication, it acts quite similarly. Instead of addition, log base b of x over y is simply log base b of x minus log base b of y. Okay, so this is the quotient rule. Your quotient as in division. Okay, so an example would be like this. If I have log base 3 of 81 over 3, I can break this up as log base 3 of 81 plus or minus log base 3 of 3. Okay. Now log base 3 of 81 is kind of big, so let me be a little creative and say that log base 3 of 81, using the product rule, I can write as log base 3 of 9 plus log base 3 of 9 using the product rule, right? 81 is just 9 times 9 minus log base 3 of 3. So this is a little bit more manageable. I can evaluate each one separately. So what power do I raise 3 to get 9? It's 2. So the first one is 2. The second one is also 2. And then the last one is 1, right? I raise 3 to the power 1 to get back 3. So 4 minus 1 is 3. So yeah, that is the quotient rule. Okay. So remember, if I have multiplication, you add the two logarithms together. And if I have division, you can split it up using subtraction. Okay. All right, so that's multiplication and division. We also have the power rule. So the power rule states that if I have logarithm base b of x to the a, so I'm raising my mathematical object, my argument, to a power a, this is the same thing as saying a times log base b of x. Okay, this is also very useful. We call this the power rule. So an example would be, let's say I had log base 10 of 10 to the 3. Okay. So if I want to ask myself, so what power do I raise 10 to get back, oh, actually, no, let's not do 10. Let's do 100. And I want to ask myself, what power do I raise 10 to get 100 to the third power? That's kind of really hard to think about if we are being serious, if we want to think about it directly. So we're going to use the power rule, which states that I can bring this 3 to the outside, to the front of the logarithm, and get 3 times log base 10 now of 100. And this looks really easier to compute, right? I know what log base 10 of 100 is, right? I'm asking myself, what do I raise 10 to get 100? It's going to be 2. So this problem degenerates to 3 times 2, which is just 6. Okay, so the power rule is, again, also very useful. That's why we're talking about it. In simplifying these large argument values, right? Because 10 to 100 to the third power is really big. It's very big. And then major the last major rule I would like to talk about is going to be the change of base rule, which basically says I can have any log base b of x, and if I don't like my log base b, I can change my base to a different base simply by doing a little bit of scaling, which basically states that if I have a log base b of x, I can change it to a log base c of x if I scale by a division of log base c of b. Okay, so you can switch log bases around just by scaling factor. It's very useful. Change of base is the name. And why is this useful? Well, it might not be that useful in terms of the scope of our class since we can't use a calculator. But if you are going forward and taking another math class like 120 or 140, where you might be given a calculator on application problems, a standard calculator will only have two base values. Like a like a relatively simple calculator. We'll only have two base values, either log base e, so ln, or log base 10. But the problems will give you will be like any arbitrary log base that's positive. Okay, so very important for us to know how to scale the logarithm bases accordingly, so we can actually compute them using the calculators that we are allowed on an exam or a quiz. Okay, so for example, I can write log base 2 of 7 in terms of log base 10. If I can't really find log base 2 on my calculator, um, TI-30, but I do have log base 10 on my calculator. I have the button for log base 10. So if I want to change it to, by the change of base formula, I can say log base 2 of 7 is equivalent to saying log base 10 of 7 divided by log base 10 of 2. Okay? So yeah, you can compute this out, and if you compute this out on your calculator, you should get approximately 2.807. That's so. And remember, we have the nice special values, so I have some special values that I would like to talk about. Remember, the range or the domain of your log base is always going to be strictly positive. So it's going from 0 non-inclusive to infinity. But the logarithm base b of any base of 1 is equal to 0, right? Because I'm asking myself, it's an exponent finder. What power do I raise b to get me back 1? It's going to be 0. And as so, this is just following from the inverse rule. Log base b of b is simply just 1 as well. What power do I raise b to get me back itself? That's 1. Okay, so those are log rules. So we have the inverse rule again. We have the product rule. We have the quotient rule, the power rule, and the change of base rule. And to help your understanding, let's try and go through the relatively straightforward proofs of these, right? So you won't be asked to prove anything on your exam. That's a little bit beyond the scope of the class, but I think it's useful in my eyes to at least know where these formulas came through, right? Logarithms are quite a difficult topic for the students in this particular class. It gets a little bit confusing for a lot. It's very common. So let's try to figure out where these formulas came from before we use them, right? So I'll prove first the exponent rule. So remember, the exponent rule says that log base b of x to the a, is nothing but a times log base b of x. I can bring my the exponent of x to the a to the front, and it be a multiplication problem. Okay, so here's the proof. So first, we're going to let log base b of x equal to y. We consider any arbitrary logarithm. But the premier example, and we'll use this quite often, this is the same thing as saying b to the y is equal to x. All right. What exponent do I raise b to get me back x? That's going to be b to the y as so. All right. Now, if I multiply both sides of the equation of this equation by a, I get a times logarithm base b of x is equal to a times y, like so. And of course, this can be written as y times a by the commutative property of multiplication. So let's call this equation 1. Now, we're going to consider the argument x to the a, right? But what is x to the a really equal to? Well, notice that we defined x to be b to the y, right? So x to the a is really just b to the y raised to the 8th power. And by the first week of class, you know that by your exponent rules, b to the y raised to the 8th power is just the multiplication of uh, the two exponents together, right? And then now what happens if x to the a is really equal to b to the y times a? If I take the logarithm base b of both sides now, I get logarithm base b of x to the a is equal to logarithm base b of b times y times a. Okay. But by the inverse rule, log base b and base b cancels out by the inverse rule, giving me just y times a on the right-hand side. But what is y? Y is simply just logarithm base b of x times a. And since these are just multiplication, I can put the a to the front, and I get logarithm base b of x. As so. And we're done, right? The last line is exactly what we were trying to prove, and that is where indeed the formula for the power rule comes from. Okay. All right. So that is the power rule. The next rule that I would like to go over is the product rule. Where does the product rule comes from? I'll put a slash here and say quotient as well because it uses the same idea. Recall that this rule is saying that either logarithm base b of xy is equal to logarithm base b of x plus logarithm base b of y. And we also have the quotient rule, right? Logarithm base b of x divided by y is simply logarithm base b of x minus logarithm base b of y. Okay, so let's prove these. Since we have two additions, or an addition of two things, it's good for us to consider uh, two definitions of logarithms. So let's define logarithm base b of x to be m and logarithm base b of y to be n. Okay, so I'm just defining these. I'm just giving these logarithms names. Okay, but by the premier example, right? Remember the premier example, right? I can switch from logarithm form to exponential form. This is the same thing as saying b to the m is equal to x, or b to the n is equal to y. Right? That's by the premier example. So if I have these cases, I can now think about multiplying x times y together. So if I multiply x times y, x is simply b to the m, y is b to the n. So multiplication of same base means you're adding the exponents together. So I have b to the m plus n on the right-hand side. Now if I take the logarithm base b of both sides, I get logarithm base b of xy on the left-hand side. And on the right-hand side, I get logarithm base b of b to the m plus n. So then by the inverse rule, the log base b and the b cancels, leaving me with logarithm base b of xy is equal to m plus n. But notice, m is logarithm base b of x, n is logarithm base b of y, so I get my desired product rule. Logarithm base b of xy is equal to logarithm base b of x plus logarithm base b of y. And that gives you my product rule. Similarly, I can also go through this for the quotient rule. Instead of multiplying x and y together, I can divide them. Division of x and y is simply just division of b to the m over b to the n. But we know by our exponent rules that division is just subtraction of the exponents. So you get the idea, right? If you take the logarithm of both sides, you get logarithm base b of x divided by y is equal to logarithm base b of b to the m minus n. The n rules, you cancel this out. So you have m minus n, but m minus n is simply just logarithm base b of x minus logarithm base b of y. As so. Okay. Straightforward enough, right? And then the last rule to go over is, of course, the change of base rule. Right? The change of base rule is useful for application problems when we only have a limited amount of log base buttons on our calculator. And recall what this is. This states that logarithm base b of x is equal to logarithm base c, another base of x, divided by logarithm base c of b. So the proofs of these go as such. Okay. So let's consider logarithm base b of x to be equal to y. Okay. By the premier example, again, this is simply just b to the y is equal to x. Then, if I take the log base c of both sides, what happens? If I take the log base c of the exponential form of this definition, I get logarithm base c of b to the y is equal to logarithm base c of x, as so. But we know that, or no, logarithm base c. I'm taking the logarithm base c of both sides, so they must match or we change in the problem. On the left-hand side, notice that I have b to the y. Since I already proved the power rule, I can put this to the front. I get y times log base c of b is equal to log base c of x. So if I divide both sides by log base c of b, I get y is equal to log base c of x over log base c of b. But y is nothing but log base b of x. As so. Of b. And we're done. Okay. So hopefully that was relatively okay to follow. Again, I just wanted to explain the proofs of these rules to help you guys understand where it comes from and hopefully make it a little bit easier, a little more trusting to use. If you're just asking yourselves why are we doing these random rules? Um, in the next section or the next part of the video, we're going to be working through a whole bunch of examples. I'm going to be doing the two exam prep materials that you are given out as of this point, which is going to be the midterm review and also I think the practice exam. I'm not too sure. So yeah, we'll move on to that in the next clip. Okay. Hello, welcome to the third part of this video. Um, this is where I'm going to go over the midterm review 3 in the modules tab for the resources that you'll need, that you are provided to prepare for your third midterm coming up on the 18th. So it'll just be me going through these problems real time. I want you to note that any problems past 19 and onwards to like 27 won't be covered on the exam because that's dealing with trigonometry and we haven't talked about that in class or in discussion yet. So you don't have to worry about those questions. We'll just do questions 1 through 18 and then go from there, of course. Do trig after the exam. But yes, so let's get to it. So for the first question, uh, oh, I also wanted to mention that this isn't the format of your exam either, right? 19 questions is quite a lot. It will definitely be shorter for an hour 15 class uh, time block. So yeah, so let's begin. We want to write uh, this object in exponential form. We know we can do this because by the definition of logarithm, there is always going to be an exponential form. And the way we do so is going to be this, right? We're going to ask ourselves, what do we raise 12 to get the argument c? So if you can invert the log base 12 by raising both sides underneath the base of 12, so that the log base 12 and the 12 cancels, and you're left with c is equal to 12 to the d. And this is your answer right here. That's just switching from log to exponential form. Okay. For 2, we go backwards, right? So now I want to find an equivalent logarithmic functions for a to the 2/5 is equal to b. So since a is the base, I proceed to take the log base a of both sides to get log base a of a to the 2/5 is equal to log base a of b. So that the log base a and the a cancels, and I'm left with 2/5 is equal to log base a of b. And that is my answer for this problem in particular. Okay. For number 3, we're going to be evaluating several logarithmic objects. So for the first one, for A, notice that log base 5 of 25 can be written as log base 5 of 5 squared. So by the inverse rule, the 5 and the log base 5 cancels, and I'm left with 2. For B, log base 6 of 1 over 36 can be written as 1 over 6 squared. But using your reciprocal rule from week 1, 1 over 6 squared is just 6 to the minus 2. And then by your inverse rules for logarithms, this is just going to be equal to 2, or minus 2. Okay. For C, remember that ln is just log base e. So log base e and base e cancels, and I'm left with just 2. For D, I have natural log of 1. Remember, one of your rules states that any log base of argument 1 is just 0. E, it's just going to be a culmination of what we did in the previous parts. We see a similar one, log base 8 of 1 over 64, similar to what we see in part B. This is simply just going to be log base 8 of 8 to the minus 2 plus 8. So the log base 8 and the 8 cancels, and with minus 2 plus 8, and that's just 6. Okay. So this, I went fast for this one because this just uses the same logic as we did up here for part B. F, log of 1 is just 0. We said taking the log of any base to 1 is just 0. G, log base 10 of 0. Now this is an interesting case. Remember, the arguments can only be positive numbers. Okay, so it can't be 0 and it can't be non-negative numbers. This is of course because the exponentials can never be 0 or negative either. So this is going to be undefined. It's outside of the domain. And so will h as well, right? -4 is a negative number outside the domain of the natural logarithm. So both the g and h are undefined. I, there's several ways you can go about I, log base 9 of root over 3. So it's pretty unintuitive to think about what power do you raise 9 to get root 3. So this is where you can use the change of base formula. So I'm going to choose to change base to 3. So I can take log base 3 of the arguments and so divide it by the log base 3 of the log base that I previously had. Okay. Remember, root 3 is equal to 3 to the 1/2. So log base 3 of root 3 is equal to log base 3 of 3 to the 1/2. And so by your inverse rule, this is just 1/2. Okay, so we have 1/2 over log base 3 of 9. Now this one you can do, right? What power do you raise 3 to get 9? That's just 2. So I have 1/2 divided by 2, which is just 1/2 times 1/2, and that's 1/4. Okay. And J, 4 log of 0.0001 is simply just 4 times log base 10. Remember, if I don't put a log base explicitly, you assume it's 10. And since I have 4 decimal spots, this is just 1 over 10,000. As so. But 1 over 10,000 is 1 over 10 to the 4, which is just 10 to the minus 4. So I have 4 times log base 10 of 10 to the minus 4. So the log base 10 and the 10 cancels, and I'm left with 4 times -4, which is minus 16. As for number 4, notice I have y is equal to ln x, and I want to do 4 things for each one. I have a, b, c, and d. I want to sketch the graph for 1. 2 is state the domain. 3 is state the range, and identify any vertical asymptotes. Okay. So for the sketch, you can be really quick about it. The only thing that I would suggest you worry about is whether or not you're placing your vertical asymptotes correctly. That's the main idea, and if you get the shape of the logarithm right. Remember, the shape of a logarithm looks like this. So for y equals ln x, we know that the horizontal displacement determines not only your domain, but also the location of your vertical asymptote. Since the argument is just x, as in x minus 0, you have a VA at x equals 0. And so the graph will look something like this. Right? It's just a sketch. You don't have to, you're not graphing it, you're sketching it. So that's for 1. For 2, we said the domain is given by the argument. We can only have positive values. So your domain is anything to the right of this vertical asymptote right here. I'll draw it in red. I'm dotting it in red. Okay. For 3, the range of any logarithm is just the real line. So minus infinity to infinity. And 4, we said already, there's a VA at x equals 0, given by the argument. Good. Number 2, for letter B, I have my sketch right here. Let's see what I have to analyze first. So I have ln x minus or x plus 2. So I'm shifting left 2 units. That means my vertical asymptote will be shifted over 2 units as well. So x equals 2 is a vertical asymptote. As such. And then you just place your graph somewhere like that, draw it, and then be done with it. All right, this is fine for this problem in particular. If I ask you to graph, of course, I would like for you to do it formally with all the steps. But for just sketching, just draw the general graph and make sure you get the vertical asymptote correctly. Anyways, for 2, the domain of this function, since I'm moving over 2 units to the left, my domain will be minus 2 infinity. And then for my range, it's still going to be the real line. And then for number 4, our previous uh, our our previous discussion tells us that there's a VA at x equals minus 2. Okay. For C, I draw my axes. I basically go from B to C is I'm just shifting down by 1. And that doesn't really change anything, just the shape. So your answers for 2, 3, and 4 are going to be the same, right? The vertical shift does nothing in terms of the qualitative behaviors, but graphically, your sketch should look at least have the indication that it shifted down a little bit compared to your answer in B. So this is minus 2 and this is minus 2, my bad. So yeah, just like make it seem like your graph is going lower, and that's fine enough for me. This is in a line, like so, or yeah, like that. So still the domain is minus 2 infinity. The range is still the real line, and your VA is still at x is equal to minus 2. And then for D, increasing the size of your base simply means that it grows faster in the small time. So you have a a faster hump. So this one's a little bit shallow. You see that this is a little bit shallow like this. So a log base 10 will grow a little bit faster like that. Okay. But the qualitative behaviors in terms of domain range and VA is still going to be the same, right? Y is equal to log base 10 of x minus 2. It's still a logarithm shifted 2 units to the left. So my domain is still minus 2 infinity. My range is still the real line. My VA is still at x is equal to minus 2. Okay. 5. I want to rewrite this expression in terms of one logarithm. So we're going to be using the culmination of your 4 rules, right? So So power rule, quotient, product, and maybe change of base. Probably not. So just three rules actually. You're mainly using power, product, and quotient for this exercise. And you're going to go term by term and simplify everything. You want to write everything as a single expression. You first need to get rid of move any coefficients to the exponent of your argument using the power rule, and then smush everything together using the product and quotient rule. So that's what we're going to do. So for the first one, I'm going to move this 4 in to get log base 10. So I can just write log of x to the 3 over 2 times 4, right? So I'm pushing it back, so I'm multiplying the exponents together. And this is going to be 3 times 4 is 12, divided by 2 is 6, plus log base x minus 3 squared, if I push that back up to the argument, minus log base z to the 6. And push the 6 back up. Okay. All right. Now, we know that adding logs of the same base means I'm multiplying the arguments together. So I can write these first two as a product in the same logarithm. So I can have logarithm x to the 6 times x minus 3 squared minus log base 10 of c to the 6. And then subtraction of the same log base is just division. So you should get log base 10 of x to the 6, x minus 3 squared over z to the 6th. That's so. Okay. So that is 5. 6 is a solving an exponential equation. I have x to the e to the x plus 4 is equal to 1 over e to the minus 2x, or 1 over e to the 2x. But notice that 1 over e to the 2x is equal to e to the minus 2x by your reciprocal rule for exponents. So your equation becomes e to the x plus 4 is equal to e to the minus 2x. And notice I have the same base now. If I have the same base and different exponents, that means I have to set the exponents equal to each other. And so I have x plus 4 is equal to minus 2x, which is just 3x plus 4 if I add over the x terms to the left-hand side. And subtracting the 4 over, I get 3x is equal to minus 4. And then dividing by 3, I get x is equal to minus 4 over 3. So, all right. So that's solving an exponential equation. We can also do the other type of equation, solving on, well, we're still solving exponential equations, right? We haven't solved the log equation yet. But let's see. So I have 25 divided by this 1 over 625 to the minus x minus 3 and 5 cubed. So I want to first notice that 5 to the 1 is equal to 5. 5 squared is equal to 25. 5 cubed is equal to 125. And 5 to the 4th is 625. That's the first thing I want to notice. So I can write all these big numbers in terms of powers of 5. The second thing I want to notice is that minus x minus 3 is simply just minus x plus 3 if I factor out the minus 1. Okay? So if I put those two together, if I change all these big numbers like 25 and 625 in terms of powers of 5, I can think about simplifying the equation quite nicely. Oh, and also, it's fair to say that 1 over 625 is equal to 1 over 5 to the 4, which is just 5 to the minus 4 by your reciprocal rule. So if I rewrite my equation, I can write 25 as 5 squared, 1 over 625 as 5 to the minus 4, minus x minus 3 as minus x plus 3, and 5 cubed can just stay the same. I can then divide divide both sides by 5 squared, to get 1 on the left-hand side times 5. So minus 4 times minus x is just 4x, and minus 4 times minus 3, that is simply just plus 12, is equal to 5 to the 1. All right? Now, if I keep going, I can invert this equation as 5 to the minus 4x minus 12 is equal to 5 to the 1. And so since I have the same base now, I can set the exponents equal to each other. We get minus 4x minus 12 is equal to 1. Adding over the 12 to the right-hand side, I get minus 4x is equal to 11, which means x is minus 11 over 4 by dividing by minus 4 on both sides. Okay. 8. I want to condense this expression as so. So again, this is simply going to be a variation of what you saw up here for number 5. We're going to be using the power rule to put those coefficients in front of from back up in the exponent, not up front, and then smush everything together using the product and quotient rules. So let's do it. 3 log x can be written as log of x to the q to x to the 3 plus log of y squared minus 9. I push that 1/2 to the exponent minus log of z squared. Okay? Now, smush these two together using the product rule. That equals log of x cubed times y squared minus 9 to the 1/2 power minus log z squared. And now smush these two together using the quotient rule to get log of x cubed y squared minus 9 to the 1/2 over z squared. Yes, so. And there we go. And 9, we're gonna go backwards now. So we did condensing, right? We did condensing. Now we want to expand out this logarithm by doing everything in reverse, right? Now what we did here was we used the right-hand side of our rules and going to the left. Now we're going to use the left-hand side and go right. So to expand, I see that I can write this as a product. I have a product of 4x and then this big term here. But first note that the square root of x plus 1 over x minus 1 is just the square root of x plus 1 divided by the square root of x minus 1. The square root of a fraction is just a fraction of the square root. That's just notation. Okay. Doing so, you can say that our term is now log base 2 of 4x plus log base 2 of x plus 1 square rooted over the square root of x minus 1. Okay? So I can also write 4x as a product of 4 times x, and this you can split up using the quotient rule. So let's do so. So I have log base 2 of 4 plus log base 2 of x plus log base 2 of square root x plus 1 minus log base 2 of square root x minus 1. Okay, so let's simplify term by term and use the fact that the square roots is simply just exponent 1/2. And we're going to use the power rule to put that out in front and make it the coefficient of the log term. So for the first term, log base 2 of 4, you're asking yourself, what power do you raise 2 to get 4? That's just 2. Okay. This term just stays the same. It's fully simplified. And the last two terms, you're just putting the square root power. So the 1/2 power out in front. And your fully expanded form should look like something like this. Okay. So don't forget that the log base here is 2. The previous ones are just log base 10. That's why we could just like go about our day, not worry about the log, because the problem only had log base 10. But this one has log base 2. So be careful. Okay. Onwards to number 10. I have the function f of x is equal to log of x minus 4 minus 1. So immediately, I can say that there is a shift right 4 units. That means my domain will be for infinity. And we want to determine the x-intercept of the graph. So by first principles, you set the function f of x equal to 0. So log of x minus 4 minus 1. So if I add over the 1, I get log of x minus 4 is equal to 1. And to undo the log, you raise both sides underneath a base of 10, right? Such that by your inverse rules, the log and the 10 cancels. And so you're left with x minus 4 on the left-hand side. And on the right-hand side, you just have 10 to the 1, which is 10. So adding over the 4, you get that x is equal to 14. So your x-intercept is at 14, 0. Okay. So a sketch of the graph can look like this. Like so. So this is your x and this is your y. This is where you graph more qualitatively, right? I'm asking you to graph now. So you label your x-intercept that you found. So this is 14, 0. You label your vertical asymptote with a dashed line and the equation at x equals 4. All right. And then your graph has to intersect this at some point. So you can have a graph that looks like that. That is sufficient. Okay. 11. We're also sketching another log graph. Here, f of x is log of x minus 4 minus 2. So there's a shift right 4 units again. So your VA is at x is equal to 4. To find the x-intercept, you set the equation equal to 0. And we'll do about the same thing, right? So you add over the 2, equal to 2. And then invert by raising everything underneath the corresponding log base. So in this case, it's 10, right? So that the log base 10 and the 10 cancels, and you're left with x minus 4 is equal to 100. And so x is equal to 104. So there's a point at 104, 0. So it's kind of big, but qualitatively you can like sketch it. It doesn't matter. The same way at least. So dash line at x is equal to 4. Label this point accordingly. And so your graph might look a little bit off, but qualitatively it's going to be significantly accurate. As so. Okay. 412. Solve for x and give an exact answer. So since I have ln, remember ln x is the same thing as log base e of x. So if I raise both sides underneath the base of e, the ln and the e cancels. So I'm left with square root of x plus 3 is equal to e to the 2. Exact answers mean no decimals, so you don't have to worry about this. You know that e is just some infinitely long decimals, but you can keep it in exact form. And we're still solving for x. So square both sides, you get x plus 3. All right, so if you square both sides, the square and the square root cancels. And this becomes e squared squared, which is just 2 times 2 is 4, so e to the 4th. So that x is equal to e to the 4 minus 3. And this is a completely sufficient answer. 13, solve for x. Be sure to check your solutions. Okay. So I have an addition of the same log base. Immediately you should think to combine using the product rule. So I'll do so. Take the product, x plus 6 times x is equal to log base 3 of 16. Now look, I have one term on the left-hand side of log base 3 and one term on the right of log base 3. So they must be equal. So their arguments must also be equal. So you simply set the inside of the parentheses equal to each other. So you have x squared plus 6x is equal to 16. And this is just quadratic. So we can solve this. So we have x squared plus 6x minus 16 is equal to 0. But this factors as x plus 8, x minus 2 is equal to 0, or x is equal to minus 8 and 2. Okay, so these are candidate solutions. We know that there's only one x-intercept for logarithm, so we have to check both that that one has to be true and one has to be false, right? But it's pretty easy to check, right? Because you see x minus 8 right here, right? It's a negative number. Look what we have here. I have log base 3 of x. So if I put negative 8 into this, it's going to be undefined. So immediately you can already assert that this is extraneous, right? Because of the negative number. Negative numbers are not in the domain of logarithm. So we check x equals 2 as a solution. So on the left-hand side, I have log 3 of 2 plus 6 plus log 3 of 2. So this is simply just going to be log 3 of 8 plus log 3 of 2. And then by the product rule, you can smush these together by taking the product. So 8 times 2 is 16, which is indeed equal to the right-hand side. So x equals 2 is a solution. The only solution, that is. All right. 14, I want to solve for x of this exponential equation. So we've been solving logarithmic equation in the last problem. Now we're going to solve exponential. Okay. So first you want to get rid of the 10 and then the 2 and then look to undo the exponential. So 2e to the 3x plus 2 is equal to 80. If I move that over, then I have e to the 3x plus 2 is equal to 40. And this is simply going to be, if I'm here now, right? Now I want to take the natural log of both sides, so that the ln and the e cancels, right? Because natural log is log base e. So I'll do so. Ln e 3x plus 2 is equal to ln 40. The ln and the e cancels. So I'm left with e 3x plus 2 is equal to ln 40. So if you subtract by 2 and then divide by 3, you should get x is equal to ln 4t minus 2 over 3. And you won't be allowed a calculator on the exam. So, but for your knowledge sake, this would be a sufficient answer. This is a fine answer. This is an exact answer, what we'll be looking for. But approximately, if you are curious, this is equal to 0.56, approximately. All right. 15 is 15, 16, and 17 are going to be application problems. Oh, and 18 as well. So we want to read the directions carefully. So we see for 15, the population is given by this function p, where t is time in years, with t equals 0 corresponding to 2005. And we want to determine when the population will be double the size it was in 2005. So double the size of it was in 2005 means that we have to find the population in 2005. We know that t equals 0 corresponds to 2005. So let's try to find p of 0, as in set time equal to 0 to find the initial population. Okay, so if I do so, I get e to the 0.025 times 0, which is just going to be e to the 0, which is just going to be equal to 1, right? Any number raised to the 0 power is just 1. So I'm just going to have 160,000 times 1 is just 160,000. So I want to know when the population will double its size. So I want to know when the population will be 320,000. So I'm going to be solving for time. So I set p equals to 320,000 to the function itself. E to the 0.025 t. And then I just solve for t, right? So divide by 160,000. So 320,000 divided by 160,000 is just simply 32 divided by 16. That's just 2 is equal to e to the 0.025t. So if I want to solve for t, I simply take the natural log on both sides and then divide by this number in front. Okay. If I take the natural log of both sides, you get ln2 is equal to ln e 0.025t. The ln and the e cancels. So you're left with ln2 is equal to 0.025t. 0.025t. So then your t value is simply going to be ln2 0.025 years. And if you were curious, if you put this into a calculator, this is approximately 27.7 years. As so. Okay. Number 16 is going to be the same idea. We're given a similar looking function, and then we're going to instead of doubling, I'm asking tripling. So it's the same idea, right? So let's move through this quickly. The initial time, because I look how long the initial bacteria count to triple. So I look for the initial population first. So b of 0 is going to be 100. E to the 0 power is just 1, so it's going to be 100. Then triple that. So I'm looking for 300 is equal to the population function. And then solve for t again. Right? So you get, if you divide by 100 on both sides, you get 3 is equal to e to the 0.33t. So take the natural log on both sides, cancel it out on the right-hand side. So you're left with ln3 is equal to 0.33t. Or in other words, t is equal to ln3 over 0.33 hours. As you curious, this is equal to 33.3 years or hours. Okay. All right, number 17. Number 17 says the radioactive element krypton 91 has a half-life of 10 seconds. An amount of krypton 91 decays according to the model A is equal to A naught times e to the kt. If the initial amount is present is 40 grams, determine the amount that is left over after 10 seconds and 20 seconds. So you know this model, right? We talked about it in class. This is a continuous exponential model. And the number in front is always going to be your initial time, right? You saw it here, right? The same type of equations. You have a number times some exponential term. And the initial time is always going to be just the number in front, right? Because you saw here and you saw here, uh, when you zero out the exponent of the exponential term, it's just one. So in this case, my A0 is just 40. So A0 is 40. And I'm saying after 10 seconds, uh, my initial amount of krypton 91 is just going to be cut in half. So after 10 seconds, a half-life occurs. So 10 seconds, one half-life is just dividing by 2. So A0 goes from 40 to 20 grams. All right. And for B, a similar thing happens, right? If A0 stays for 40 or for 20 seconds, it first goes through one half-life at 10 seconds. From 0 seconds to 10 seconds is uh, 10 seconds. So one half-life occurs. And if I go through another 10 seconds, I have my amount again. So I now have 10 grams. Okay? That's really that simple, right? Reading the directions is just a small line of work. All you had to do was recognize what a half-life meant. And since I gave you two full half-lives, it's simply just having your initial amount, A0, which is given to be 40 grams. Okay. And then for the last one, as in the everything else is just trig and we won't cover it, is another a another another exponent another application problem with exponential growth. Okay, so the logistic growth function is given by f of t. It describes the population of an endangered species t months after introduction to a non-threatening habitat. And the first question asks, what is the initial population? So of essentially solve f of 0, set t equal to 0. That's what initial means. So 2000 over 1 plus 3e to the 0 power minus 4 times 0 is just 0. And that's just 1. So you really have 2000 over 1 plus 3, 2000 over 4, which is just 500 species. 500 species. So the units here is just like members of species. So, and then what is the limiting size of the population as t grows to infinity? As in what happens if you look at this quantity right here, what happens as t grows to infinity? Well, we know that e to the minus 4t is equal to 1 over e to the 4t, right? So as you increase t, as t gets larger, as t gets larger, the number in the denominator grows larger. It goes really big. So you have like e to the 100,000, and you keep going to infinity and whatnot. And so you have one over a really big number, and that's really close to zero. And it actually just goes to zero infinitely. Um, so this term, right here goes to zero as t goes to infinity. And I'll show you a pictorial on Desmos to illustrate my point. Um, if this goes to zero, that means I have 3 times zero as t goes to infinity. So really, as I go to infinity, as t goes to infinity, I have 2,000 over 1 as my population, which is just going to be 2,000 members of the species. Okay. So what does that mean in terms of what's happening to the population? Well, if you think about it, if I start my initial population at 500 and I grow all the way to 2,000 and never more, it sort of acts as the max that the max population a species can have in a certain environment, right? If you think about it realistically, um, in like a finite amount of space, populations can't grow on forever, right? There must be a max because there's a limited amount of space and resources and food and shelter. So there must be a max. And in population dynamics, of course, there is going to be logically that max. And its special name is called a carrying capacity. And so this 2000 represents a carrying capacity, as in no matter how long you go through in like a perfect setting in a fixed amount of space, your population is never going to exceed a max amount of members. And in terms of what the graph will look like, let me share my screens. So this is the Desmos graph. Well, first of all, that's the function we have, but let's look at e to the minus 4x first. So if I zoom in, let's go all the way. I need to, yeah. So e to the minus 4x, you can see that as you increase x, I'm taking x to be t in this case because Desmos can't recognize t as a variable. You can see that it gets really, really small really quickly. Like really, really small really quickly. It says zero, but there is computational error. It's not actually zero. It's just really close to zero. You see, as you zoom in, keep zooming in, it's a really small number, like 2 times 5 to the minus 10 to the minus 9. That's a really small number, but that's not really zero. It's really close to zero, but it's not zero. But as you increase uh, your t, or in this case your x, even just a smidge towards infinity, it goes really quickly to zero. So that's why this bottom term zeroes out. But in terms of the function that we looked at on Desmos, you can see that, oh, let me go back up. If you graph this on Desmos, you can easily see that there's going to be a initial time at initial population at 500, at time zero. But as you zoom out, as I zoom out, you can see that after a while, your population just levels off at 2,000. And this is not actually 2,000, but it levels off to 2,000. It just gets really, really close. You can see the decimals. And that's the idea, right? This isn't actually 2,000. It's just there's rounding error. Keep zooming in. Um, oh, hold on. Well, but yeah, it says 2,000 here, but you have to trust me that this isn't actually 2,000. It just levels off because you saw that the e term was getting like really close, like 10 to the minus 9. The idea is that there's an asymptote, a horizontal asymptote at 2,000 that it doesn't exceed. Um, but yeah, that's the graph, and that's just basically going to be the gist of how to solve these application problems. Um, so yeah, that's So that concludes this part of the video, solving these two, or this midterm review 3. Not quite as indicative of what you'll expect on the exam. You still have to cover sections 3.1 to 3.6, which is everything other than exponential and logs, right? Like talk about polynomials and rational functions, not just exponential and logs, which is the new stuff. But yeah, so stay tuned for more resources, I guess. And we will pick up later.